Well, scientists have just reconstructed one of the biggest volcanic eruptions in Earth's history, and the more they dug into it, the worse it got. Over 350,000 years ago, the center of New Zealand's North Island looked completely different. The mountains we see today weren't there yet. The climate was colder, and the region was literally stuck in an ice age. Winters were harsh, and temperatures stayed low year-round. Everything looked calm and quiet, well, on the surface. Underground, something was building and building until it snapped. A supereruption hit the Taupo volcanic zone, the Whakamaru eruption, one of the biggest ever recorded on Earth. Now, it wasn't a single mountain that produced it. It was a whole volcanic system stretching from Wakari White Island in the north toward Ruapehu in the south. A weak zone in Earth's crust was getting stretched and broken at the same time. One force was pushing magma up, another was pulling the land apart. That combo powers this region even today, but back then it got extreme. The eruption blasted so much material that ash spread across huge parts of New Zealand. In some areas, it was so thick that it buried the land under layers of volcanic rock and debris. It was like dumping miles of powdered stone over a country. Today, that same zone hosts hot springs, bubbling mud pools, and steam vents. And all this sits on the top of the same, if a bit quieter, system. The Taupo volcanic zone has been active for about 2 million years, having produced at least 4 supereruptions. Those weren't small events. On the Volcanic Explosivity Index, they hit level 8, which is, so far, the maximum category. We've only had a few dozen such eruptions on Earth. The most recent one was the Aroa Nui eruption about 25,300 years ago. That one was even bigger in volume and created what is now Lake Taupo. In other words, Whakamaru wasn't a random disaster. It's what this volcanic system does from time to time. Supereruptions are still one of the hardest problems for scientists. Because how does a huge amount of magma sit underground, build up, and then just explode almost at once? To figure that out, researchers read the leftovers, ancient deposits. There are 2 main types of those. One is flow deposits, left by fast-moving avalanches of superhot rock, gas, and ash called pyroclastic flows. All that mass rushes along the ground like a burning flood and later solidifies. The other kind of evidence comes from fall deposits. Those are lighter materials like ash, crystals, and volcanic glass. They get blasted high into the air and then rain back down to the ground. Now, the problem is time. Most of these deposits don't survive. They get eroded, buried, and broken apart. What's left is often scattered across huge distances. The Whakamaru supereruption left exactly this kind of mess behind. Huge pyroclastic flows form thick layers of dense volcanic rock across the Whakamaru and King Country regions. Farther out, ash and pumice spread much wider, covering large parts of the North Island and even reaching into sections of the Pacific Ocean. To piece all the traces together, researchers first had to track down where the fragments actually came from. They built a database of volcanic deposits and matched them using a chemical signature. You can find it locked inside tiny bits of volcanic glass. Each eruption leaves a slightly different chemical mix. Using that method, scientists checked more than 30 sites across New Zealand and the South Pacific. And even though the samples were spread so far apart, they all matched the same source, the Whakamaru supereruption. So, finally, researchers could piece together what happened during one of the biggest eruptions in Earth's history. At the start, the central North Island likely had a large lake in the middle of it, similar to modern Lake Taupo. Then, magma broke through the surface right into that water. That's where things escalated fast. When magma hits water, the water instantly turns into steam. That can make an eruption extremely destructive, and it's probably what kicked off this one. At first, one huge magma chamber was likely feeding the eruption, but soon the situation changed. The eruption continued, and the lake was destroyed and filled in by volcanic material. And once the water was gone, the style of the eruption shifted. It became drier and more direct. And underground, something even bigger was happening. Instead of one magma chamber slowly emptying, the system split into numerous active zones. At least 5 separate magma bodies may have started erupting at the same time. The ash output became extreme. Most of the North Island and even distant Chatham Island ended up under roughly 12 inches of volcanic material. Closer to the source, up to 15 feet of deposits covered the ground in some regions. Then came the pyroclastic flows, fast-moving currents of superheated gas and rock. Near the eruption zone, they left behind deposits hundreds of feet thick. When you add everything together, the numbers are hard to picture. The eruption blasted out roughly 550 cubic miles of material. If you spread it evenly across all of New Zealand, the entire country would end up buried under about 30 feet of volcanic debris. But the scariest thing is that the Taupo volcanic zone is still one of the most powerful volcanic systems on Earth. Supereruptions like Waikumaro are rare, but the system has produced many smaller eruptions too, and those are capable of reshaping large regions too. That's why this research matters not only for geologists. We must understand how these eruptions switch from single-source magma to multi-chamber catastrophe. This way, we'll be able to figure out what such a system is capable of doing in the future. And New Zealand isn't the only place where scientists worry about giant volcanic systems. One of the most famous examples is Yellowstone in Wyoming, Montana, and Idaho. Some experts think it might be overdue for a massive eruption. The last one happened around 70,000 years ago, according to the U.S. Geological Survey, and the last true supereruption occurred about 640,000 years ago. And yes, the volcano is still active, even though not in the imminent disaster way most people imagine. You can see that activity right on the surface. The Grand Prismatic Spring is the biggest hot spring in the U.S. and the third largest in the world. Its famous bright colors come from bacteria living in different temperature zones around the spring. The water itself hits about 158 degrees Fahrenheit. This spring is boiling, and volcanic activity is what's driving this process. The magma system below Yellowstone is massive. It may be even larger than we thought earlier. If it fully erupted one day, it could release around 2,500 times the energy of Mount St. Helens, and that eruption was a devastating event. In 1980, a 5.1 magnitude earthquake triggered the north side of the mountain to fall away, which created the largest debris avalanche ever recorded. The blast flattened about 230 square miles of forest and took the lives of 57 people. Anyway, all that underground activity doesn't mean Yellowstone is ready to blow tomorrow. In fact, it gets about 700 to 3,000 small earthquakes every year, and most are so weak that people don't even feel them. It's just the ground constantly shifting and adjusting. But if a full supereruption ever happened in that region, it would be a full-blown disaster. First, pyroclastic flows would rip through parts of Montana, Idaho, and Wyoming. Then the ash would start falling. It would spread across the entire U.S. Roofs could collapse under the weight of all that heavy ash in some areas. Air quality would drop, and water systems would get contaminated. Such a chain reaction could trigger a global food crisis, but it's just a hypothetical situation at the moment. We should remember that even though supervolcanoes are terrifying, they're rare. It's often the smaller volcanoes we should look out for.